So these are the position variables, and these are just the data of the four metric, the 3+1 data of the four metric, and you see explicitly that all those quantities in action depend on this set of data, completely determined by this set of data. Well, and this R, of course, is completely determined by Qij, and this Kij depend on Qij and I, and of course you should have the time derivative of Qij, and also depend on the lapse function n. And well, K is just the trace of the Kij. All right.哎，吉同学，你那块没有录吧？
录上了，刚刚忘了。
All right. So this is the position variable, and because as I said, so to do the Hamiltonian analysis, we have to give momentum variable. Okay, so we have to define momentum variable. Momentum variable is just the conjugate. I mean, so for any position variable, there is a momentum. And so firstly, so if we make the functional derivative of the Einstein-Hilbert action with respect to Q dot, remember, well, I mean, let me first give you the most general. P equals to, well, this is definition, delta action delta Q dot. Yeah, so I mean, the action depends on the time derivative of position variables. You just make the derivative of your action with respect to the time derivative of the position variable, and which the result is the momentum variable. Okay. All right, and in our case, so what we call Pij twiddle. So there's a reason that I put a twiddle. I will talk about it. So this is the momentum variable conjugate to Qij. So this is delta as Hilbert divided by delta Qij dot T and X. Okay? So everything depends on time and also depends on space, space-time field. Okay? And similarly, you can recall Pn twiddle T X equals to delta as Einstein-Hilbert delta n T X n dot. And similarly, P twiddle n vector, and so there's an index I. I. So this is the conjugate momentum for the shift vector. Okay, so we got three different types of momentum variable, but because we are considering a field theory, general relativity, gravity is a field theory. So everything, all the variables, all the position variable, and all the momentum variables are fields, are space-time fields, depending on both T and X. All right, so here maybe I talk a little bit about the functional derivative, how to calculate this functional derivative. I mean, in usual classical mechanics, probably only need to compute the ordinary derivative, but for field theory, you need to compute this kind of functional derivative. So maybe I give you some additional remark about functional derivative. So it means that suppose we have an action. Well, this action is a functional of some field phi, and so I put a index A. So because the field, maybe not just the field, but bunch of field. Yeah. So this phi A is the field, so it's phi a, which depends on space-time x or x mu, space-time x. Yeah, and then these, so therefore, if we do the functional, the variation of this action, yeah, so what we get will be, suppose our space-time is d-dimensional, you will get some function ga x and then delta phi a of x, right? And this, then the, suppose you want your equation of motion, the equation of motion is just the dAx equals to 0, right? And we will consider any action and consider any variation, and you always write your action, your variation of action in terms of this form, and which is proportional to, which is linear to this delta phi a, and you have a quantity, some quantity in front of delta phi a, also inside the integral, and your equation of motion is just ga x equals to 0. And this is just your knowledge of variational principle. Okay, and then once you have this formula, so then you can have the functional derivative. You can define the functional derivative by a x just equals to ga of x. Okay. Well, you can consider analog with ordinary derivative. Yeah, and this delta s into the, so here you have an integral because your field is, you have infinite number of fields. You have infinite number of degree of freedom for the field. But you can suppose you make analog with finite with system with finite number of degree of freedom. So this delta s will just reduce to ds. So you consider some analog, ds equals to sum over I ga I and d phi a I, right? You see, and the difference between infinite number of degree of freedom and finite number of degree of freedom is just yeah, and here you have integrate over x, and here you only have a finite sum over I. Yeah, and so this is just ordinary in your calculus. This is just ordinary differential, ordinary total differential, right? And from this formula, you can read, of course, in your calculus that partial s plus partial phi a I equals to ga I. Yeah, so this is standard knowledge from calculus. So here, the functional derivative is just some kind of generalization from finite sum to integral, and then the ordinary partial derivative will become so-called functional derivative. So here you can view this x is just some label, just like this I. It's just this I is finite, so you have finite sum over I. So here x is infinite, so you replace the summing over x is the integral. Yeah, and the derivative becomes functional derivative. As a special case, you can consider phi a itself. So yeah, this is just something related. Okay, so this is d, but this phi a of x you can write as the integral of phi a x as well. Yeah, so this integral is just the integrating delta function. So x prime and delta d x minus x prime and delta ab phi b x prime. Yeah. Okay, and you have this formula. Then of course, if you do the variation of this formula, you view this guy is your previous s, and you consider the variation of this formula. Of course, you will get x prime delta d x minus x prime b delta phi b x prime. All right. So now you know you can compute the functional derivative of phi a x with phi b delta phi b x prime. Right. Okay. Then from the above, calculation, you know what it is. It is just delta d x minus x prime and delta ab, right? Okay. So this is also analog. Suppose you want to compute derivative, partial derivative. Yeah, I'm coming from compare this side with finite dimensional integral, finite dimensional derivative. I b j. Right hand is just a delta ab delta ij, right? Okay, so you see, and the left hand side, the functional derivative is just the infinite dimensional generalization of the finite dimensional partial derivative. Okay, so this is some remark on how to compute functional derivative. So and you just need to all the time apply these kind of rules to actual calculation. All right, so now you just apply these functional derivative to compute those quantities, compute those functional derivatives. Okay, and this is really, again, I leave you an exercise for this. Let me see. It is, yeah, this is very easy. You see, you capture when you compute the conjugate momentum with respect to q dot. What you can capture is just this term, right? And you get two of this term in Kij and Kij. Yeah, you just compute the derivative, and what you can get is Pij twiddle equals to determinant Q Kij minus K Qij. Yeah, and maybe I first give you the Pn and Pn vector, and here you observe that actually you can't find Pn dot. You can't find n dot and ni dot in the formula. So here is a speciality of Einstein-Hubble action, is that here you find for those position variables, and some position variable has time derivative in the action, but some variables has no time derivative in the action. Yeah, for n, for lapse function, you can't find, you see all those formulas. Yeah, these three-dimensional curvature only depend on Q, doesn't depend on n and a. And Kij depend on n, but only spatial derivative. It's no time derivative. Yeah, and K, yeah, it's just a trace of Kij. So there's no n dot. Yeah, it's only depend on n and spatial derivative of nj. There's no n dot and nj dot. Yeah. So here, what you get is that the momentum for n dot for n and the momentum for vector n for shift vector is actually 0. So this here p twiddle n equals to 0, and p twiddle I n vector equals to 0 as well. Okay, so we got those momentum. So let me. So again, it is your homework to derive them. Write down homework, derive them. For the last two result is just trivial. Okay, and yeah, the first equation give you the relation between p twiddle ij and other configuration variables. Sorry, I think there is a yes. Oh, okay. So here this Kij. So here it relates to Pij, p twiddle ij, q, and here this k contains this k, ij, and k contain q dot ij and n and ni, contain other quantities. You see, and you remember the definition for Kij. It contains n, q dot, and nj. Well, it also depends on q because this is the covariant derivative. Q dot and also qij. Depend all those variables. So and this Pij, it is symmetric. It has some symmetric properties. It is symmetric when I replace 2j. Yeah, it is a symmetric tensor. So if you like, this Pij is component of a tensor. It's not, yeah. Well, but second remark is that it's not exactly a term. It's not exactly a tensor. So it is not really a tensor. So this Pij, although look like it seems that it's just it has Ij, it's a matrix. It seems that it may be a tensor. Maybe the component of tensor in the coordinate we have specified. But actually, it is not. The reason is that it contains a prefactor of determinant Q. Because of it is not. So firstly, it is even if it was a tensor, it would be at least just a spatial tensor. It has no way to be a space-time tensor because this Ij only has spatial components. And furthermore, it is not even a spatial tensor because of the prefactor determinant Q. The reason is that you can easily see the transformation rule of this quantity. It's not a tensor transformation because you see this Qij definitely it is tensor and this Kij is also a tensor. So I mean, the quantity inside bracket it is tensor, but this square root determinant Q it is not a tensor because square root determinant Q, if you change the coordinate and this quantity, right? This determinant Q and Q itself is a tensor. Then determinant Q transform into determinant of Q prime and multiply the Jacobian matrix square. Jacobian matrix is like determinant partial x prime square. Yeah, so it transforms like that. But as you see in tensor in the transformation of tensor, it doesn't have this kind of factor, this kind of determinant of Jacobian. It doesn't involve in the coordinate transformation of tensors. Yeah? So therefore, the coordinate transformation of this guy does not coincide with the coordinate transformation rule of tensor. Therefore, it is not a tensor. Yeah? But it has a prescribed way of transform. You just add to the tensor transformation a prefactor, which is a determinant of Jacobian. Okay, so it's still transformed in a nice way, in a prescribed way. Okay? And this quantity, it is actually called tensor density. This is called a tensor density. Tensor density of weight 1. Of weight 1. Okay? So it is called the tensor density because the tensor transforms in the previous manner, but here this tensor density is you can view this some sort of new quantity that it transforms like a tensor, but not exactly as a tensor, but it transforms with additional prefactor determinant of Jacobian. So the rest part transform in a tensor, but because you have the square root of determinant Q as a prefactor, so this quantity transforms in this way. Yeah? So which means you just add to the definition of tensor some prefactor of determinant of transformation Jacobian. Yeah? So once the quantity transforms in this way, this is called a tensor density of weight 1. Or it's also easy to see that once you have a quantity, it equals to a tensor multiply a determinant of square root of determinant of metric. Then it is a tensor density of weight 1. Yeah. Suppose you have a certain power, you have a square root determinant Q to the power m. then it means it's a tensor density of weight m. So I will talk a little bit more about it at some point about this, about tensor density. Yeah, and actually you have seen that, and you have seen why you need that in the integrals. For example, the Einstein-Hilbert action. Yeah, this Einstein-Hilbert action. Yeah, this in the bracket is a tensor, but outside there's a square root of determinant of metric. So again, this is a tensor density. And the reason why you have a tensor density in the integral because you are integrating over four-dimensional coordinates. Yeah, so the entire quantity is coordinate independent. Okay, so that's the interesting part of the tensor density. So here, because your Lagrangian is a tensor density, then of course you're taking functional derivative of your action with respect to a tensor. The result is still a tensor density. Yeah, so here it is what you get. This is what you get from momentum. And secondly, so this is the first some interpretation of the first formula. And let's talk about the second two equation. So here you get trivial result for momentum with respect to n and momentum conjugate to n vector. And actually these two quantities, you can view these two quantities are sort of constrained. So these are called primary constraints. Primary constraint. So from this calculation, you immediately get two primary constraints. So how to understand them? So this is our, suppose this is our phase space. Phase space. Yeah, and I'm sure you have learned phase space in your classical mechanics. And you know the phase space, of course, in classical mechanics, probably you only learn a two-dimensional phase space. One dimension is the position, and the other dimension is momentum. But here, of course, now the phase space is infinite dimensional because we are dealing with fields here. So okay, so you have one direction of the phase space, one set of direction phase space, which are the configuration, the position variable, qij, ni, and n. And then the other independent directions are momentum variables, p twiddle, ij, pn, pn vector. Yeah. So I mean these are, if you view these, those are coordinates in the phase space. So phase space is also a manifold, but this is just infinite dimensional manifold. And you have coordinates, so those q and p's are coordinates in phase space, and also they are functions of phase space. Okay, so now the constraints just says that, so here you get those coordinates of phase space, which are conjugate variables, position and momentum. But here immediately from getting momentum, you find two primary constraints, and which means you are somehow already in a you have to work on the sort of constraint surface. If you like this constraint surface where Pn equals to Pn vector I equals to 0. Well, I mean, there is a special notation for Hamiltonian theory. Hamiltonian formalism is that, I mean, when a function is constantly 0 on the entire phase space, we say, let's say f equals to 0, it means that this function equals to 0 on the entire phase space. Yeah. Suppose we say f curly equal to 0. This doesn't mean approximately equals to 0. It just means that this function equals to 0 only on the constraint surface. Means equals to 0 on, it means the constraint surface. So it means equal to 0 on constraint surface. So this is equal to 0 on entire phase space. equals to 0. Yeah, so this is just some kind of notation which is frequently used in Hamiltonian analysis. Okay, so here we have some constraints. So it means that our system for general relativity, when we talk about Hamiltonians, it has constraints. So it's a system with constraints. Probably in your classical mechanics, you have studied some system with constraints. Okay, so these p equals to 0, Pn and p vector n equals to 0. They are called primary constraints. So which means you already specify a certain constraint surface. It means you can eliminate certain coordinates, these two coordinates from your phase space. Then you come to a lower dimensional, simpler phase space. All right. Okay, so then we have the momentum, right? At least the most useful momentum is the first formula. Then the next step is that we have to solve Q dot. So according to the standard Lagrange Hamiltonian analysis, is that once we have the momentum, a momentum depends on Q dot, of course, and then we have to solve Q dot from momentum. We have to solve this equation for Q dot. So we can solve Q dot ij. So the result is solve Q dot ij from P twiddle ij. And the result is the following. Q dot ij equals to 2n. So over there this is just that is just a linear equation linear relation between Pij and Q dot ij. So it's very easy to solve. Twiddle minus 1 half P twiddle Qij plus 2 Pi nj symmetric. So Qij is a symmetric tensor. So spatial metric is a symmetric tensor, and Pij is also symmetric. So that's why here you need a symmetrization of ij. So this formula I will call it star. I will use this formula later on, of course. So here P twiddle, it is just, well, by the way, this twiddle simply means, okay, so here I forgot to say that the reason I put a twiddle is just a standard indication of a density. So here you put a twiddle on top, it usually means that it is a tensor density. You have a single twiddle means that it is a tensor density of weight 1. Right. So this P twiddle ij, it is a scalar density. It's just the P ij twiddle Q ij. This is just the trace of Pij. So again, it is your homework to derive this, but it's very simple. Derive this. Okay. So now what we are going to do is so-called Lagrange transformation. Lagrange transformation. Okay. And so we are going to write the Hamiltonian formalism, the Lagrangian of Einstein-Hilbert action into a Hamiltonian formalism. So as Einstein-Hilbert equals to 1 over kappa. So here I put kappa back. 3x. And the Lagrangian of Einstein-Hilbert. So this is what we call Lagrangian density. Because, well, this just equals to R multiplied minus G. This is what we call Lagrangian density. And this equals to, what we do is, okay, so this we are going to write it in terms of Hamiltonian. This is Pij Qij dot minus H script H and this script H we will call a Hamiltonian density. So this is, it's not a derivation. This is just a sort of reformat, rewriting. Okay, so this is a Hamiltonian formalism of the action. This is actually our goal of the derivation. So, and then from this formula, you can read the relation between H and Lagrangian.
Okay. For the first attempt, it would be P tutor. For the first attempt over the action, yeah.
Yes.
Yeah.
And okay, so from this formula, you know, H equals to just Pij Q dot Ij minus Lagrangian. Okay, and now because now this H has to be only a function of this. So P twiddle Ij Qij n vector n I. Yeah, and because the momentum variable of n and I are 0. So anyway, so this Hamiltonian has to be a function of momentum and position only. It should not depend on Q dot. Yeah, so that's what we call Lagrange transformation. The Lagrange transformation transforms the Lagrangian, which depend on Q and Q dot, to Hamiltonian formalism, where the Hamiltonian only depend on P and Q. So now, which means that for the previous Lagrangian, in the Lagrangian, we have to replace Q dot, and in this formula, we have to replace all the Q dot into P. Yeah, which means we have to use these formulas called star. So it means we have to plug in star for this formula. Okay, and let me give you the result. Again, it is your homework to derive this formula, but this is really simple. Just plug in the previous formulas. The result is n multiply minus square root determinant q r3 plus 1 over q ij 1/2 square. So here you have it involve upper ij and lower ij, and of course the index ij are raised and lowered by qij, by spatial metric. And plus 2 pij little d I nj. So this is the result of the Hamiltonian. So this formula I will call A. This formula I will call formula A. Okay. Again, this is your homework. Derive this. So yeah, the homework of this class is just filling all the gaps of the lecture. Derive this. All right. Now, once we have, this is the Hamiltonian density, and then the spatial integration of the Hamiltonian density give you the Hamiltonian. Which I use H equals to 1 over kappa, integrating on sigma d3x Hamiltonian density. Well, now I can write this formula in the following format. So I can write this as integrating sigma d3x n multiply c plus ni multiply ci. Yeah, why I can do that? So I mean, n multiply c is very clear. So yeah, so This is just this term. So inside square bracket, I will call it C. Yes, and n multiply C. And this term is it's a little bit different from n multiply Ci, because here nj is inside the covariant derivative. But what we can do is always making integration apart, moving this covariant derivative from ni to Bij. Yeah, and it's up to a total derivative, of course. It's up to a total derivative, but this total derivative will be a boundary term. Yeah, so we always ignore the boundary term. So let me say this equals to this plus boundary term. Boundary term. All right. So now let me write down what is C and Ci. C. So C equals to 1 over kappa. Q, and both C and Ci are very important quantities, as you will see in a minute. J minus 1/2 p squared minus 8. Okay, and here Ci equals to kappa, so minus 2 over kappa Pi p little ij. Okay, so you see, actually, if both of them are still densities, yeah, both C and Ci, they are densities, yeah, because H is H is inside the integral, and H must be a density. Well, for example, H is P twiddle ij q dot, and Q is a tensor, and P twiddle is a density, and then it must be a density. And Einstein-Hilbert action, as I said before, Einstein-Hilbert Lagrangian density, yeah, this is a scalar density. So therefore, C is, it must be a scalar density. So but because but I didn't put a twiddle. It's just a convention. So someone usually sometimes can put a twiddle on, but I just want to make formulas very clean. And also in most literature, people don't put a twiddle on C and Ci. But you should keep in mind that both of them are actually densities. So here you can quickly see that it depends on square root of determinant Q. It's a density. Let me say, put a label. I think this formula I would call B. Let me see if I should